Ladies and gentlemen, boys and girls, aliens and DMT entities alike tuning in from all over the cosmos to Vilbiati, welcome to Max Depth. We have our wonderful friend, Yupen, joining us today, and I couldn't be more thankful. So thank you for coming on and talking to me. I really appreciate it.
Thank you for having me.
Yeah. So I thought we should start at the beginning because that's where any good thing starts. I think that's a reasonable place to start. Could you talk me through some of the early influences, maybe when you were a kid, and how they shaped your thinking, how they shaped your worldview, and how they influence you on the career that you've eventually taken and some of your early interests?
Yes, yeah, certainly. Hello, everyone. I'm Upen. Growing up, I think one of the biggest influences that I had was one of my uncles and one of my cousins, and both of them were physicists. So the uncle has since then passed away, but my cousin is still around. And they were both deeply passionate about physics. My uncle, he was an engineer by training, and his day job was as a mechanical engineer.
Mm-hmm.
But he was deeply interested in physics, particularly in relativity.
Mm-hmm.
And he used to do all of these experiments at home. He himself was never really convinced about the theory of special relativity.
Wow.
I don't know why.
Huh.
But the great thing about it was he would devise all of these experiments to convince himself like that there was nothing wrong with it. And of course, growing up, I did not understand all the details, right?
Sure.
As a kid, you don't like special relativity. Even today, really, I don't completely get it.
Uh-huh.
But his passion, do their day job, come home, and then just keep working on these experiments. He published a couple of books. I sort of limited success, but they were really they were the labor of love, right? It was
Mm-hmm.
it was less about sort of actually proving Einstein wrong or getting any sort of publicity out of it.
Mm-hmm.
It was just his own personal passion.
And where did you grow up?
I grew up in India. I was born in India. I grew up in Bombay. It's now called Mumbai. So it's a very large city,
Mm-hmm.
very busy, a very different place.
Mm-hmm. I've never had the pleasure of visiting India, but my dad grew up in Hong Kong for 17 years when he was a kid, so
Oh, wow.
he talks about India very fondly. That's cool. So when you would go home and you would see, what would the experiments look like? Was he would he have a white lab coat on, and would he be pouring solutions into each other and watching smoke rise up, or?
So most of them were experiments with light, because special relativity
Mm-hmm.
is really all about right, the speed of light
So that was
and
his main
frames of
focus,
reference. Yeah. So he had all of this equipment which was really about measuring the speed of light under various conditions. Eclipses used to really excite him because that is a time where you can see phenomena that you can't see otherwise.
Mm.
So particularly like the moon when it occludes the sun, this is slipping more a little bit into general relativity
Mm-hmm.
than special relativity.
It's okay.
But basically the moon, because it is it produces an effect on the gravitational field,
Mm-hmm.
light bends a little bit,
Mm-hmm.
right? So every total eclipse, you actually get a little bit of proof of general relativity.
Because the light bends around the moon?
Yes, yeah,
Wow.
sun's light, as it is approaching the earth,
Mm-hmm.
it actually bends a little bit. So you should, if there was no relativity and if light wasn't bending,
Mm-hmm.
the moon would have completely covered the sun,
Mm-hmm.
but you see a little bit of light coming through
Mm-hmm.
because the light is getting bended.
Interesting. Wow.
So it's a fascinating sort of field, and the nice thing about those kinds of experiments is they require very little investment, right?
Mm-hmm.
Really anyone could do that, and that is how really a lot of the early physics happened.
Mm-hmm.
So you have like Maxwell and even like going all the way back to Newton. There's Maxwell, even some of the early experiments in relativity, electromagnetism, even quantum mechanics. All of them were done on really shoestring budgets. It
Mm-hmm.
was nothing like, they didn't have a particle accelerator like the CERN particle accelerator, which
Mm-hmm.
is billions of dollars.
Mm-hmm.
None of that. It was just people sitting in a lab thinking about things, measuring things very, very carefully.
And to think that we're still like that laid, like we stand on the shoulders of giants, like they laid such a foundation with such limited tools.
Yes, it's amazing. I mean, and a lot of these folks were not even, again, physics was not their main occupation. They were almost always doing something else, and this was really their hobby. And they would, through whatever means they have, keep inventing and keep discovering.
Do you think there's something to be said that it wasn't their main occupation, that they were involved in other things, that they had kind of ideas coming at them from a lot of different angles and weren't in, I mean, I imagine as like a researcher you wouldn't find yourself in a silo because that's not the type of thing that would lend itself, or a researcher wouldn't find themselves doing to themselves, but just getting ideas from a lot of different places, what do you think about that?
No, that's a really good point. I think a couple of things happen there. One is, even I think all of us experiences it is, if we are forced to do something or if we are required to do something, it often takes the joy away from it, right? I mean, you're a student, you know this, like if the professor is making you study some material,
it's so much less enjoyable, even if it's something that I would be learning about on my own.
Exactly, right? And I when I was studying, I would often, like, after my finals were done, if I just read all of that stuff again, I would just enjoy it so much more. But just the sort of the pressure of like finals and so on, it makes it, so there is that part of it, that if it was part of your job, sometimes, not always, if you don't have the right environment, it feels more like a job than as a vocation, right? Something that you are inherently called towards. So there is that aspect. And then there is the other thing, like Newton, all of these folks were also sort of, they were a different kind of people, in the sense that they did not just specialize in physics, not just in like maths, calculus. They were all over the place, right? They were really poking and prodding at every sort of different stream of knowledge. So I think those kinds of people are rare, and then there may be some of those around even these days, but it's just given sort of how deep you have to go into any subject to be an expert these days. I don't know how sort of impactful their work is today.
Of the early academic interests, was it physics that first interested you? Was it, and maybe how did you get from whatever those early ones to computer science?
Yeah, that's a good question. So yeah, physics was sort of my first love. I even when I was like 10th grade, 11th grade, I would, back in the day, there was no internet, right? You couldn't find information easily. So the place where you would find information is the library. So I used to love going to the library. In my town, I probably read all the books in the local library. Then there were these like bigger science libraries, so I would go and find the right physics books there and just go and read them.
Would you take the bus?
I would take the bus. So it was a fun time. I mean, I used to really enjoy finding those books, and each book that I discovered, it would be like, oh my god, I can learn this new thing about something. So yeah, that is how I started out with physics. But then I started realizing a lot of the things that I was interested in also overlap with chemistry. Right? Nuclear physics and nuclear chemistry are pretty much the same thing at the end of the day. So physics and chemistry were both very interesting, and mathematics primarily because it's sort of the foundation to both of those disciplines. So those were sort of what I used to focus on. Computer science was not, of course, taught in schools when I was growing up. So my first exposure to computer science was, or maybe in the 11th and 12th grade. And what I really liked about it was very mathematical. It was very, very well structured, and it just sort of felt like studying computer science would actually open up way more doors than just studying physics or studying chemistry, because even back then sort of a lot of actual practical physics work had moved from people sitting down and doing things by hand to computational physics and computational chemistry and computational biology. Like at the end of the day, there's only so much that the human mind can process very quickly. You really need computers to speed up things. So it felt like, okay, computer science is actually something that can open up just so many doors. So yeah, that is how I got into computer science.
Beautiful. So the beginning, we started off our conversation last time talking about, you're explaining what I understood to be the most fundamental, the starting point of mathematics. Is that right? Can you expand on that?
Yes. So the last time we talked about the foundations of mathematics, and it's a fascinating history. Again, I'm able to recall only certain portions of it, but let me tell you about the bits that I recall. So mathematics, as you can imagine, like it's in different cultures. It started out in very different, from very different places. Ancient Greeks, of course. There's Socrates. There's Plato. There's Aristotle, and even folks before that. China had its own sort of mathematical discipline. Even like India, of course, did. Even before that, Mesopotamia, they had mathematics, and a lot of them came from very practical places. Like they needed to measure land or build things, and that is how they worked out. Like how do you actually build a pyramid, and that is where they learned a lot of their math. But it was really ancient Greeks who first got into more of what we would think of as abstract math. And then I think it really starts with Plato, his theory of essentialism, in which he looks at the sort of, I'm paraphrasing here, but the idea is every physical object that you see is essentially an imperfect form of some perfect form, and then those perfect forms can be expressed mathematically. So let's say a circle, right? Any circle that you draw is likely going to be slightly off. While there is this concept of a perfect circle in math, right? So that perfect circle, that perfect sphere, you have your Platonic objects, right? So all of those, Plato, essentially his theory was there's a world that is independent of this physical world that we live in, which is the mathematical world, and that is sort of the more pure form of it, and everything in reality is essentially a projection of it, in some sense an imperfect projection of it. And he of course had very strong opinions. He did not believe in irrational numbers, and the first time irrational numbers came along, this was after I'm confusing Plato with Pythagoras, by the way. Okay. Yes, irrational numbers is the person who really did not like them were Pythagoras, and he this is after he died, but his disciples, when the first irrational number, which is square root of 2, came around, which is basically because it's the length of the hypotenuse for a triangle, a right angle triangle that has sides of 1 unit each. That is when they could not understand the concept of an irrational number. So every time math ran into these sort of fundamental sort of blockers, something new was invented. Of course, at that point, irrational numbers were invented and understood, and so on. So math moved from this very practical, sort of very reality-based science into more and more into an abstract world, where things like irrational numbers and imaginary numbers, things that have really no sort of, you can't map it to human experience, right? The human brain can't really understand. We understand real numbers. We kind of understand integers. But rational numbers, irrational numbers, it starts hitting the boundaries of what the human mind experiences in real life. But we can express it through the language of mathematics. So then they kept sort of building on top of that. Philosophy and logic was another way that came in. You started expressing logic through mathematical language. So that is where you have first order logic and so on. And at some point they started realizing that there's a common basis to things. So So for example, what we learn as algebra in schools, it's really what is called elementary algebra, because you're looking at equations and variables and quadratic equations and so on, right? That's elementary algebra. There was geometry, there was number theory, and all of these, they started noticing that the underlying basis of it was one. You could actually take things and express them through some underlying basis. So for example, set theory, it is an underlying basis through which you can express various concepts in geometry, various concepts in elementary algebra, in number theory, and so on. So they started noticing these more foundational objects, mathematical objects, sets, and so on. And then there was a thought that maybe everything in math can be expressed through this formal language. So there was, in early 20th century or late 19th century, early 20th century, there were a few folks who believed that mathematics could be completely represented in a language, in a formal language, which is completely self-consistent. And then they went down that path, and that is where they started hitting a few paradoxes. So last time we talked about, I think, Russell's paradox, which is in set theory, you can say that, let's say R is a set.
Okay, R is a set. Let's go slow on this part.
Yes.
R is a set.
R is a set
of objects.
Of objects.
Okay.
And those objects are sets themselves.
Okay, sets within sets.
So it is a set of all sets that are not members of themselves.
Okay.
So let's sort of pass that. So it is a set, and the elements of that particular set are sets with the property that they are not members of themselves.
Okay.
So the paradox there is R a member of that set? So if R is a member of that set, then R can't be the set. That set can't be a set of sets which are not members of themselves.
Okay.
And if you say R is not a member of that set, then that also leads to a contradiction. So basically, this formulation is not self-consistent. Like R can either be a member of that set, but it violates the property of the set definition, or we are saying it is not a part of that set, which violates the definition of R itself. So they ran into these sort of, and this you can express it as using very simple set notation, right? That this is R. So then they found out, like, many such paradoxes came along, and they realized that there is, in the language of mathematics, there are these missing pieces where you can't actually have a self-consistent language. So that is where there was like, it was apparently a very heated discussion among all mathematicians at that point. Some of them believed, like Hilbert, that it is still possible. We are just missing something, and it is still possible to figure out that formal language which is completely self-consistent. There were some folks, I think Brouwer was one of the lead proponents there. They believed that all of this is a meaningless exercise. It doesn't actually matter if math is self-consistent or not. What is more important is the applications of mathematics. And then there were folks who were sort of trying to bring both of these worlds together, saying maybe there's a way to express things formally, but let us look at where that applies to more practical problems. And then again, scientists, mathematicians, they're all humans. Apparently this was like an actual heated debate where Hilbert tried to get Brouwer out of one of the mathematical, like, editorial boards. Like, it became like a personal conflict between them.
It's a real knife fight out there.
It is a real life fight out there. So it must have been a very interesting time to just be a fly in the wall at that time, right? Observing sort of all of these mathematicians fighting it out.
And how does Gödel come in?
So Gödel, yeah. So he was in the camp where they were sort of really probing the limits of this formal language. Like, where does it break down? Where does it not break down? So Gödel he had his incompleteness theorem. So what Dilbert did was he laid out a set of sort of almost challenges that were needed to be solved in order to lead to this complete theory. And he was a brilliant mind, by the way. I mean, one of the most brilliant mathematicians ever. And he laid out these challenges, and various people were sort of poking at different challenges there. And Gödel looked at the completeness problem. So there was sort of, he was working on that. At the same time, there were folks like Alonzo Church and Alan Turing, and they were approaching that same problem from a different angle.
The same incompleteness problem?
So yeah, it was, I think, essentially around 5 or 10 years, that same time frame. So I think Gödel first sort of put out the incompleteness theorem, and then it was followed by sort of Church and Turing looking at what is sort of computable versus what is not computable. And both of them, so Church was Turing's PhD advisor. So both of them worked closely together. Turing was, of course, he came from the UK. He did his undergrad at Cambridge, and then he moved to the US, to Princeton, and Church was at Princeton, and the two of them I think collaborated a bit, but the two ways in which they approached this problem, they approached it independently. Church approached it through what is known as lambda calculus. So again, it's a system of mathematical logic.
Okay.
And then Turing approached it through the angle of a computational machine, what is known as a Turing machine. And the idea there was they were sort of probing sort of what is actually computable versus what is not computable, because that is one of the limits of mathematics, right? As in, are there problems which are just not solvable? Are there problems that are solvable, but they are just going to take so much computational power and so long that for practical purposes they are not solvable?
Okay.
So all of that really started out with Church and Turing's sort of work, and that is really the genesis of what we think of as computer science. Is their foundational work there.
So what would they have thought of pi? Would they think it was a solvable thing, or would they Yoshibak, who I mentioned to you earlier, who's amazingly brilliant, he said that he thought of pi as a function, and I always thought of pi as a number that I was trying to memorize up until the 100th digit of in fourth grade. So I thought I was cool for it. What would they have thought of that?
So yeah, that's a very good question. My guess is they would have thought of it as a function as well, because that goes down to sort of this foundational aspect of mathematics. So if you look at numbers, right, let's say natural numbers 1, 2, 3, 4 and so on, in mathematics, sort of those are things that numbers are something that we are very, of course, familiar with through human experience. But if you really look at what are the properties of that particular set, at the end of the day it is a set, and what are the properties of that particular set, it has specific properties. It is associative in mathematics. So associative means if you have a plus b plus c, and if you draw the sort of the parenthesis around a plus b plus c, and then that is still equal to a and plus b plus c, right? So it has the associativity property. It has identity. Right? The number 1 is identity in natural numbers.
Identity is a starting point.
It is a starting point,
Okay.
right? I mean, one specific identity has a very specific definition. If you say multiply anything by 1, it's still that number. So that I think is the definition of identity.
Okay.
Is it's a number within that set, or it is an object within that set, that if you do a operation on it, a binary operation on it, you still get the other number, the other object in that binary operation as a result.
Mm-hmm.
So there is, within the set of natural numbers, there's this identity. So natural number actually is, you can think of it as a very specific kind of a mathematical set.
With specific properties.
Which has specific properties. And there are other things in nature which have similar properties. So certain geometric structures, for example, they you can think of them really as that property, that kind of object. So that is where things in mathematics, if you take set is a very general concept, but you can use that as a basis to define more specific kinds of objects. So there's, for example, an object called a magma.
I've never heard of a magma.
Yeah, which is just it's a set where you have, that is probably very esoteric objects, but we may have heard of things like, maybe this is also esoteric, but like semi-groups, groups, rings, fields, and so on. So these are all specific kinds of sets where you say it is a set of objects and certain operations can be defined on them. Where the common operation is, say, addition and multiplication, and that they follow certain property like associativity, identity, commutativity. It's sort of it's a lot of details, but the idea there is, at the end of the day, you can express so many different things as saying, oh, this is a group, this is a field, this is a ring, and suddenly whoever, like if an alien lands here and they don't understand what you mean by natural numbers, but if they understand groups, you can tell them, oh, it's just a group with these properties, and they will be able to get that. So it's sort of a more fundamental way of thinking about things.
Okay, and so the fact that all of those exist, does that mean that all of them are implementable? Does that mean that the universe must have like the compute power, the framework to be able to compute all those things?
So some of those things, but not some other things. So that's where it gets really interesting. So for example, irrational numbers like pi, for example, you can express them as this particular set of irrational numbers which has certain properties, right? And you can say, is it associative, is it commutative, is it distributive, and so on. So that is where I going back to your question, I think that is where I think those folks would have seen, say, pi or any other irrational number through that lens, that, oh, it is part of this set of objects that have these common properties, and pi is just one of those numbers. So in many ways it takes away sort of the specialness of certain things, and it makes us realize that a lot of things actually have far more sort of common, more foundational basis to them.
And going back to Turing, going back to the computing framework, can we resume there?
Yes. So Turing, for example, laid out sort of one way in which computation could work. So this is what was known as a Turing machine. And it's intended to be, again, this is late 1930s, early 1940s, right? So again, computers did not exist there, of course. So the way he laid out this computing machine, quote unquote, is it is basically an infinite tape with symbols. And the symbols, you can think of it as zeros and ones, right, as a simplest set of symbols.
Okay, so it's a tape with an alternating set of, or maybe not alternating, but just random set of zeros and ones.
Yes, it is some set of zeros and ones. And what that machine is doing is you're basically telling it to either read whatever is the tape, sort of whether it's a 0 or 1, whatever is the symbol at that particular position.
Okay, so it reads a 0.
It reads a 0, or it can advance. So that is another operation.
Okay, so it has two possible operations it can do. It can either read or skip.
So I mean, it can read and skip. I think they are separate things. So you can say it reads things, it skips, it moves to the next position. And again, it can move forward and backward, if I remember it correctly. And it can also do certain, I think, basic operations. Like if it read 1 and then it moved and it read 0, and now it can do an operation with that 1 and 0. So let's say an addition or something like that. So it is a very, very simple sort of mathematical framework on how you would actually store things, right? Because it's a tape, so you're actually storing things, and how we would process things, because you are now reading that 0 or 1 or whatever that symbol is and actually doing operations on it. And that was almost revolutionary, because it gave people a way to not just sort of lay out things as they existed, but actually look at how things could be computed, right? So until then, computation was a human enterprise. Like the term computers, actually during World War II, it used to refer to people like who worked
that
out
were the
math,
computers,
and mostly women who actually did all the calculations and so on, and they had very rudimentary calculators to do that. So computers used to refer to people, but now suddenly there was a model in which you can say, okay, I have this problem I need to solve, let's say a very simple addition, but what I can do is I can express it as this machine which actually does that computation for me. And then the next sort of phase of it was, how do you actually build this machine? So Charles Babbage, this is 19th century, he had built what was known as the analytical engine, so a very early version of a very massive calculator. So there had been work on building these kinds of machines which could compute things, but then it really took off with Turing's work. Turing himself worked on a machine in Bletchley Park, so he was involved. He was a cryptographer. He was involved. He was one of the people who solved the Enigma. Are you familiar with the Enigma machine?
No,
so basically, Germany.
I've never heard of the Enigma machine.
Yeah. During World War II, sort of things had advanced a lot in terms of warfare, and of course it was like Germany was. They had tanks, they had submarines. It was a very advanced military power, and one of the most advanced things that they had was advanced cryptography. So they could write sort of messages from headquarters to the field
that could be decoded, that were written with certain operations and then decoded with the same operations. And
they had these specific machines called the Enigma machines, where it did certain. So you took the plain text message, like say attack at dawn, something like that, and you actually codified that using that machine. So it was a machine. Operating that machine was relatively straightforward. And unless you had the machine, and unless you knew some information on how to decode that, you couldn't actually. You needed that machine on the other side to be able to decode it. And one of the early sort of successes in the war was that the United States and the UK actually got their hands on some of these Enigma machines without Germany realizing it. Germany, I think, thought that they had been submerged or something. They went down with one of the boats that got ships that got shot down.
They intercepted a missile. Was it to Mexico? Maybe I feel like
I forget. Yes, I think they intercepted some of the messages, and a lot of the work that they did was how do you actually reverse engineer this machine so that you'll be able to decode German communications. And that is where they set up sort of a group of really brilliant mathematicians, again a lot of them women. They were working off of this place called Bletchley Park in the UK. It was a old sort of manor, some aristocrat's home, I think, that the government took over during the duration of the war, and that is where all of these folks got together and they were trying to break this cipher.
Interesting.
And Alan Turing was a big part of that particular effort, and that is where he sort of made the connection between these very practical uses of sort of the computational sort of the framework that he was developing, and it's sort of very practical use case. So they were able to break that code. They were able to reverse engineer the machine, and it was a very, very top secret thing that they actually knew how to decode it, because they couldn't let the Germans know that, right? Like if Germany found out, they would have changed the machine, and this advantage would have been lost. So in fact, they allowed certain battles to be lost just so that Germany did not realize that they actually had broken the code, and it gave them so much advantage in in the war, and then that is really part of why World War II was won by the Allies.
Wow.
It's sort of the work of these brilliant mathematicians and cryptographers.
Mm-hmm.
So Alan Turing was coming from sort of all of that background,
Mm-hmm.
and after the war there was this huge push to actually build these machines. There was really a race because Soviet Union was in it, the USA was in it, UK was in it. Who could build sort of these big computational machines? The big driver at that time was, of course, the nuclear race, as in who gets first to the hydrogen bomb, and then all of this involves very complex calculations.
Mm-hmm.
So you really needed big calculators, if not computers.
Mm-hmm.
So Alan Turing at Cambridge, they built one of these large machines. In the US, some of these large computers were being built out. So there was another set of sort of scientists. Von Neumann is one of the people who were doing that very practical work of actually building these machines.
Mm-hmm.
So what you see in computer science is that very interesting thing where you have theoretical computer scientists like Turing. Turing was really an applied scientist,
Mm-hmm.
but like folks like Alonzo Church and so on, they were coming from a very mathematical background, right? And trying to prove things in mathematics and really somehow almost stumbling into computer science.
Mm-hmm.
And then you had very practical folks like Charles Babbage and his daughter, and later Von Neumann,
Mm-hmm.
who were coming from this very practical perspective of we need to really build these large calculators.
Mm-hmm.
And those two things come together with sort of computer science and programming languages.
Mm-hmm.
It's still seen today like the theoretical folks, they came from a very mathematical background, so there is a stream of languages called functional languages.
Okay. In computer
In
science?
computer science.
Okay.
And those have very they're really mathematical languages that you can write programs in. And then there are very sort of languages that came from a very practical, like we need to code these machines, like how do you make these machines operate, and C++, these kinds of languages, they are more called imperative languages.
Okay. So was it functional and imperative languages?
Functional and imperative.
Okay.
So again, those have that root in the Second World War and
the
war
two
that
different
happened.
streams of thoughts that kind
And
of.
it's two different.
Mhm.
So you still see them sort of being played out even in my day-to-day work. I see it being sort of very interestingly played out that I'm using functional languages for certain things, imperative languages for certain things. Even the people who kind of use it are still sort of, there are people with a mathematical bent of mind, and there are people who are more sort of electrical engineering bent of mind. So it's you can still see that same sort of dichotomy being played out even today.
Mm-hmm. Can you take me from, I guess, classical computation to maybe cloud computation, and then maybe quantum computation, something
Yes,
like that?
Yeah, certainly. So classical computation, again, it began, it had basis in these large calculators, and then they were building out ever larger of these calculators. So the first computers were massive.
Mm-hmm.
They would be in these large.
And why were they so massive? What was contained in the massive computer?
Yes, yeah, that's a good question. So fundamentally what you need in a computer is essentially what we call a gate. So
the transistor.
A transistor, right?
It's
And
like saying whether something's a 0 or a 1.
Exactly.
Uh-huh.
And then something that can take that 0 and 1 and do something with it.
Uh-huh.
Right? So there's a transistor piece which provides you the basis for both the computational aspects, like how do you do addition, how do you do subtraction, how do you do multiplication.
Mm-hmm.
So that computational aspect, as well as the storage aspect,
Mm-hmm.
because it can actually, you can have transistor or similar components which can hold on to that 0 or hold on to that 1.
And do the transistors store the memory?
So it's essentially, you can think of it as transistors or similar components, but basically a transistor,
Okay.
right, which can store that information as well.
Mm-hmm.
It really depends upon how long you need something to be stored.
Okay.
But early on, you could also use a transistor to store. And the very first devices, they were called vacuum tubes.
Okay.
And then they were actually sort of almost like electric bulbs. They were actually tubes that were vacuum sealed, and you had an element in there. So very physical, large components. And the larger computation that you need to do, the more of these transistors you needed. And that is why computers were just getting bigger and bigger in size, because you needed these large physical units to actually do.
And at that point, the size of the transistors were fixed?
The size of the transistor was fixed, because it was this physical element where you could only shrink it down to so much, right? Because it actually there's a physical element with a small vacuum glass.
So now is there no physical element?
That is where there was sort of progress started happening on can you implement this transistor using something else, some other material, and so on. And that is where people moved away from these vacuum tubes. They moved to more semiconductor based transistors.
Okay.
So semiconductors, you may know from physics, basically it's silicon, germanium, those particular metals.
Okay, silicon and germanium.
Silicon, and those are the common semiconducting materials there.
Okay.
And they have certain properties which lend them well to be able to build transistors. Essentially these elements which can either sort of do this computational side of transistors, or they can hold on to a 0 or a 1.
Okay.
So all of that was again work in solid state physics. So again, lots of deep work that happened in physics and in chemistry to make all of that possible. But that is where you started seeing the size of a computer shrinking down. But it was still these massive, like even in the 70s, before personal computers came along, it was still a room-sized mainframe computer. Personal computers still shrunk it down, but there was always this physical aspect to a computer, right? Even when I was in college, if you actually needed to say run a massive experiment, you actually needed computers in your lab. So you had to go by, we had to write all of these grants where NSF or some NIH, some entity would give us money to buy these physical computers. You had to then bring those physical computers, power them up. You needed space to host them. And that is true for all industries, that every industry needed to buy their own computers and essentially use them for whatever purpose they needed to use it for. But the challenge with that model is there's a lot of upfront cost. Like if I need to do some scientific experiment, and I'm a bank and I need to run my sort of banking application, I need to first purchase all of this equipment, and then all of that equipment is going to stay around for 3 years, 5 years, right? So I'm committed to that long-term investment. And what that meant was the barrier to entry to do anything.
Yeah, progress, right?
I mean,
so high.
It was so high. Like you needed that initial investment, otherwise you were not going anywhere.
Yeah.
And that was a huge blocker to innovation. So where cloud computing really came from, it had a very interesting journey. I mean, different research folks were also working on it. They were approaching it from more of a shared infrastructure perspective. Like universities, as you know, are always cash strapped. So they were trying to pool together the resources, saying, I can't put in this upfront thing, but if we pool together our grants, let's buy 100 servers, and then each of us can time share them.
Okay.
Like you get it on Sundays, I get it on Mondays, that kind of stuff. So universities were approaching it from that sort of shared infrastructure perspective. They called it grid computing back in the day. Lot of companies were also looking at something like government provided facilities where it could be a shared infrastructure. Companies like Amazon actually approached it from a different angle, in that Amazon is a retail website, right? And it has this daily pattern, a diurnal pattern, where people are shopping during the day, but not as much at night. There's also a weekly pattern where a lot of people shop at specific days during the week.
And then, of course, seasonal patterns where
seasonal,
people
right, exactly.
shop more during Christmas
like
and the
Black
holiday.
Friday and Cyber Monday. Those are like the peaks of Amazon. Now Prime days are also peaks. But then the infrastructure is just lying idle the rest of the time for the most part.
Okay.
So they had this huge problem. Like, what do you do with all of this infrastructure that you are going to need
sometimes
on Thanksgiving, but not be before that or after that? So that is where the idea was like, can we actually let other people use it safely? So that is where, for example, Amazon started its cloud computing journey. But overall, this was coming together in the sense that you want to make computing a utility. Just like electricity is a utility, power is a utility, water is a utility. And utility in the sense that it is, you pay as you go, as in you only pay for electricity, you switch it on, right? And then once you're done with it, you switch it off. And you only pay for the time that you're actually using it.
Yeah, Bezos said pay by the drink, pay by the glass. I was like,
pay by the glass, right? You don't say that, this light or whatever I need it, I'm going to actually have a 5-year upfront cost for the electricity that this is going to consume. That just would not make sense. So that is where utility computing came in, that you just want to make computing a utility that people pay for as long and as much as they need, and then they stop paying when they don't need it. And the other aspect of utilities is also they are very reliable, right? I mean, the amount of engineering that goes on in making the power infrastructure work, the telecommunication infrastructure work, the water, and all of these critical things work, it's just amazing. They have gotten it to a point where it is very, very reliable. And that was another goal, that you want to make computing that reliable, that you can run critical services on top of it. So that is where really cloud computing came into being, is that this idea that we need to lower the barrier to entry. So we need to make it easier for people to innovate. And so that is from the sort of the innovation angle. And we need to utilize this excess infrastructure that a lot of companies like Amazon have. And those two things just met in the middle with cloud computing. So what cloud computing really is you can, so there's a computing part of it where you can say, I want to use a server for an hour today. And you go to whichever cloud provider you want, you get a virtual machine for just that hour, and at the end of that hour you shut it down and you only pay for that hour. And what the cloud provider is doing behind the scenes is it has this infrastructure that is shared across all of its customers, and it is managing it in such a way that you and I, if we are running on that infrastructure at the same time, we are doing it safely. Like, you can't see what I'm doing, I can't see what you're doing. Even these cloud providers can't see what either of us is doing. So we can share that infrastructure safely, and when we are done, we no longer need to pay. So then the cloud provider's problem becomes, how do you they take care of sort of managing this infrastructure, understanding how much capacity do you need, right? Are the two of us going to use it at the same time on Monday, or are you going to use it on Monday morning and I'm going to use it on Monday evening, and then it's okay to have just one machine, or do I actually need to use two machines? So they take care of that complicated capacity problem. They take care of securing everything. They handle that entire underlying infrastructure. And then if I'm a startup, I don't have to worry about any of that, right? If say my startup is all about ride sharing, right? Something like Uber or Lyft, I can focus on actually the ride sharing part of it, and I don't have to worry about, do I need to go buy 100 servers, and what is going to be, do I need to build, like, how do I build a database? Like, I'm not a database expert. I know ride sharing, I don't know databases. So it lets you sort of have this division of responsibilities, where some people are taking care of the underlying infrastructure, and the others can therefore focus on their business, what makes their business unique and makes them distinct from their competitors.
do you just find that model that AWS devised just amazing?
It is. I mean, it was game changing. I think no one anticipated that it was going to be this successful. But I think it has just proven that it is a very good model. And of course, there were other companies that got in, and it was that competition that also had really defined what cloud computing is today. But it really helped sort of, I think, innovation. It had sort of jumpstart a lot more of small companies and startups, something that would not have happened if cloud computing wasn't around.
And do you see computing kind of scaling in size, or do you feel like there are fundamental leaps that could happen over the future time period that are going to change maybe how cloud computing is done, or just how anything is done?
Yes, yeah, that's a good question. I think in terms of size, there's really no shortage of problems. The bigger a computer you can build, that you'll have a problem that you can. There are so many existing sort of very practical problems that can't be solved because there is not enough computational power in the world.
Okay.
So, like for example, just weather forecasting, right? It is extremely complicated computational.
Yeah, we were just learning about this in my my science.
Nice.
Yeah, the slight changes to initial conditions cause huge diverging results.
Yes.
That's why, like the flap of a butterfly's wing, if the storm is going up the East Coast, the projections are so massive and the storms are so unpredictable. And that's the compute is the bottleneck.
So yeah, so I think so multiple things. One is, of course, you need the right sort of input data.
Yeah.
So that is where all the ground-based radars and satellite radars, all of those things help. You of course need the right density of those, right? Unless if you have a very sparse density, which is true for say some of the underdeveloped nations, that is where the forecasting is just not going to be as accurate. So you of course need a lot of the right kind of input data there, but you also need to be able to process all of that information and sort of model that in the right way and compute the forecast there, and that requires a lot of computational power. So that is why, for example, today things have gotten really good. Like weather prediction is really good, but the more computational power that is available, the better it will get. Right? Even today, it is a little bit hit and miss, right? Say rainfall prediction, what have you. But if bigger computers are available, they'll be able to do that. So there's no shortage of problems that could be solved with larger and larger computers. It is always a matter of is the cost making sense, right? I need to solve this weather prediction problem, but if I need to invest $10 billion more,
is it worth the
1% accuracy? Is it worth it? So as the cost of computation goes down, then instead of $10 billion, it becomes $1 billion. If it becomes 1 million, then like of course I'll spend $1 million to get that accuracy. So there is that natural sort of progression that will happen with the existing computing technology. But then you also talked about quantum computing. Right, and that is
can I pause so fast? It says low power. Because I'm going to go for a little bit longer if that's okay.
Yeah.
I just want to plug it in real fast.
Yeah.
Thank you. There we go. Let's see. Power up. Let's see. I don't know how that plugged in because it's just not plugged in.
Oh,
that's pretty interesting.
Yeah,
we can do this though. This should be able to give us a little bit more juice. All right, let's try that. Boom. Let's try cloud computing.
Yes, yeah. So, the next frontier really is quantum computing, and the idea there is today with the computers that you have, you either can hold the state 1 or 0, right? That is how typically things are set up. But you can't, and then even within, if you really look at the sort of electrical engineering and solid state physics side of things, even that 1 and 0 is not sort of that binary. It's the actual,
it's not.
Yeah, the actual device, it has, let's say it's a voltage based thing. There will always be a threshold. So let's say 0 to 0.5 volts, that will be defined as 0, and 0.5 to 1 volts will be defined as 1. And the actual voltage could be, say, 0.2 or 0.7 or whatnot, but it is not sort of always at a voltage of 0 or a voltage of 1.
This might be kind of an out there question, but if quantum mechanics is like a substrate that the whole universe is running on, how could there, I guess, is that the reason why a fully binary system, like could a strictly binary system be implementable or no?
So I think it is implementable. It may just not be practical or cost effective.
Okay.
As in, you could insist that the voltage either needs to be 0 or it needs to be 1, and those are the only states that you recognize, and if it falls anywhere in the middle, it enters into this unrecognizable state.
And that just wouldn't be useful. Okay.
It won't be useful. You would need a lot more sort of backups to say, oh, what was its real state? Was it meant to be 0? Was it meant to be 1?
And so in quantum computing, is there still the Turing machine reading each position? And so when it encounters the 0 or 1 that's on, it's a superposition of either the 0 or the 1, and then how does it go from there?
Yes, yeah. So I think the quantum computing, again, I'm not an expert in quantum computing, but the idea there is you really use these sort of quantum states to say that any particular, they call it a qubit. It doesn't have to be a 0 or a 1, but can have many more states between 0 and 1 almost. And that way you can store a lot more information in that 1 bit than you would be able to store if it was either a 0 or a 1.
Interesting.
So it suddenly sort of opens up that entire dimension in which growth could happen in terms of computational power. So it is still sort of the Turing machine, of course, it's a model, a mental model. The real computers are both more complicated than it, and in some ways simpler than it, because certain things that would be allowed in the Turing machine world, for example, won't be allowed in a real computer, just for practical reasons. But like you can't have an infinite tape, right? Which is the model that you have in the Turing machine. But the idea there is, even with that same model, it is now you have a lot more symbols that you can have instead of just 0 and 1. So quantum computing is, the idea is that it will just really open up a huge dimension in which we had not explored computational power, and it would make solving of sort of very hard problems tractable. The challenge, of course, is it's very early days. It is a lot more progress needs to happen before it sees sort of practical uses. But again, you have to try. There are some skeptics as well. They believe that quantum computers may never be able to achieve even sort of the power that you have with today's computers, and that may be true, right? There are, I think, certain fundamental limits to how much energy you can sort of produce, and then you start running into real sort of physical constraints, and so it is possible that quantum computing may never actually achieve this full potential, but we have to try. That is why a lot of people, very smart folks, are working. They're starting at a very basic level, but you necessarily need to start there so that you can work your way up.
Yeah, I guess kind of wrapping up, I wanted to I don't know about rapid fire because I don't have a storage of questions like that, but just as they come to mind, I was thinking about just popping some questions to you and just like kind of seeing
let's do that.
If you weren't pursuing the problems that you're working on now, are there other problems that you that you would be that jump out at you that you're like, oh, I wish I had more time. I wish I had a team and money that I could dedicate to this problem? Are there like is there something in like renewable energy or bio or what other things are interesting you that you just feel like kind of constrained by, but that would be interested in pursuing or like would love to see more work be done on?
Yeah, that's a really good question. I think at least three things come to mind. One is, of course, our times the biggest challenges, as you point out, at this time are there's a climate change crisis and a related but separate crisis of loss of biodiversity. Right, we are losing species at a very rapid rate. Some of it is driven by climate change. Some of it is not driven by climate change. It is driven by other human activities and choices. But those two are the problems to solve at this point of time. So yeah, if I had the time and resources, I would work on those. The third thing, which is perhaps it is vanity really, more than anything else. But and then maybe vanity is not the right term, but selfish interest. But it is the problem of aging and death. Right, I think humanity, of course, our average life expectancy has grown quite a bit, but there are some very tantalizing, so there's tantalizing research which shows that you could actually prolong human life by much longer, and then healthy human life, not sort of
healthy human life is the key point. Like, have you done much research into that area?
Not a whole lot, but yeah, I mean, the quick 2 cents are everything is speculative. The only way we know to slow down aging really is exercise and eating well, right, and taking care of yourself. There's no other magic solution known as of
fundamentals.
Now. Yeah, fundamentals. But then beyond that, I think people are really looking into why does sort of aging occur and why does cellular death happen, and are there ways to stop it or reverse it and so on. So I think that would be a very fascinating area of research, and of course a lot of money is being poured into it. A lot of the rich people don't want to die, really.
Yeah.
So
Altos Labs, I saw Bezos just gave, or a few years ago, gave $3 billion. I also was really interested in that question for a little while, but I can't even speak because after this period of not learning about it for a while, I understood some of the work being done to prolong aging at one point, but it escapes my mind because it was so much that I was kind of memorizing for a conversation I had like this with someone that was working at one of those billionaire that didn't want to die funded laboratories in I think San Francisco, which was interesting. But I got a little exposure to that, but that's a really interesting area. And I don't know if this is the same answer or maybe not. If you could have, I mean, this is out there. If you could have the answer to any question, what would it be?
Ooh.
Or maybe a set of questions, or maybe a few questions if you don't want to choose just one.
So, I mean, again, this goes back to something that you mentioned at the very beginning, right? Which is, I mean, as humans, the fundamental thing that we grapple with is sort of what is our place in the universe? Where do we come from? So the question that I would really like to know the answer to is, why does the universe exist? Right? Isn't like that seems to me to be the very fundamental question, that if we knew the answer to that, like a lot of things would just explain themselves after it. Like there is no reason for the universe to exist, but it still does exist. So why does it exist? And that is again where mathematics, there's a very interesting thing between sort of mathematics and sort of the other fundamental sciences like physics, chemistry, and biology. Is all of those other things are about investigating the universe as it exists. Right? Physics that does not look at this universe does not make any sense. But mathematics almost exists, or it does exist independent of this universe. Like even if this universe did not exist, all the 1 + 1 would still be 2. Like the mathematical concepts, the mathematical world will still apply, be true. Like if gravity worked differently in the universe, math would still be the same.
So mathematics would be discovered and physics would be invented based on this our context?
Yes, exactly. Like I said, math is something that exists fundamentally in some sense, while everything else is a result of a particular configuration of the universe. So it's a sort of fascinating question, like why does the universe exist, and why are there things that are sort of almost extra universe, right? Like mathematics. So yeah, that would be the question that I would like to know the answer to.
Yeah, and maybe one last one would be any advice if you could go back in time to your past self. If you would, I don't know if we haven't talked about family at all. If you have children, what would be some of the things that you would teach them about how to be a great human being, or maybe live a meaningful life, or any things that you would that you just feel are fundamental things that kind of have shaped you and that you hold really that you put a lot of value into?
That's a good question. So I'm single. I
Ladies, baby, woo! Or
yeah, guys. So yes, but yeah, I think the advice that I would give people is be kind always, right? I think every person sort of comes from a different sort of personal life experience background. You don't know exactly what any individual person is going through. So always be kind to people. I think that is sort of my motto. So yeah, that is what I would tell my kids if one day I have kids. Thank you.
And we might have missed the best part, but something's recording. So thank you. Beautiful. Thank you very much.
This was so much fun.
I'm glad you enjoyed it. I loved listening and loved talking to you. Thank you. Yeah, that was great. Good job.
Thank you. Yeah, I don't think I've talked this much in a very long time.